In the earlier class, we have started our discussion on magnetic field in material medium and is for introduced the magnetization vector, which is the induced dipole moment for unit volume. And we first stated that the field at a point, the magnetic field at a point, is due to the field of the due to the conduction currents within the conductor and due to the magnetic field due to the magnetic material. This conduction current is due to the free currents, so this is called BF free, and this magnetization is due to the bound charges and bound electrons, so these sometimes are denoted by the subscript B. Another one thing, note that these bound charges moves in specific orbits within the electron, so there is no chance of scattering, so there is no loss effect. Here we shall try to establish a relation between M and the currents. You know that this magnetization originally arises due to the circulating or orbiting electron, is due to the orbiting electrons. This magnetization is due to the orbiting electrons, because the orbiting electron produces dipole moments, and sum of the dipole moments per over a small volume per unit volume is the magnetization. Now we want to connect this vector quantity with something which have the sense of circulation. So to say, the quantity we look for a quantity Jm called the magnetization current density. Volume density. Magnetization current density Jm. We want to relate it with this. So there should have been some relation between two vectors. So the relation must at the same time there must be some relation through the curl operation, because circulation is involved. That is, the relation should be like this: either Jm is equal to curl of M, or the reverse, or M may be related to curl of Jm. These are the two possibilities. But if we check the relation dimensionally, we found that this is not a possible relation, so the relation should be of this sort. Let me first establish this relation. In doing this, we shall first take a elementary treatment. We shall adapt an elementary treatment which will give me insight, but at the same time there will be some points to object mathematically, and in the next in the second attempt we shall adapt mathematically rigorous treatment. We consider three volume elements whose center are A, B and C, and this is the coordinate system denoted. So the A and B are the two volume elements, similar volume elements. Means each of has the volume delta V is equal to delta X, delta Y, delta Z. This is the delta X, this is delta Y, this is delta Z, and this is delta X. The coordinates axes are shown here. So we have considered three adjacent volume elements. The volume elements A and B are displaced along y-axis, while A and C are displaced along x-axis. If we take the picture from down the z-axis, it looks like this: A and B are displaced along the y direction, A and C are displaced along x direction. we take the point A, that is the central point of this volume element A, as the reference point. So the coordinates of A is this, and that of B is x y plus delta y z, and that of C is x plus delta x y z. So these are the three adjacent volume elements. If we consider these two volume elements, so the face that appears is the yz yz plane. Let me draw these two. This is A, this is B, this is y direction, this is y direction, this is z direction, this is x direction. So if we look down this along the along the x axis, what appears is these two. So this phase is the x is equal to constant phase. So the magnetic moment, the magnetic moment that is of concern is the x component. So we write the dipole moment, or dipole moment of a volume element is mxa delta v, because m is the magnetization vector. The subscript a refers to the fact that it is at the within the volume element A and at its central position, that is this, and x means its x component. So dipole moment per unit volume multiplied by delta v is the dipole moment of the volume element A. On the other hand, we can define it in a other way. If we look down the z axis, the current flowing through it is in this direction, and we call it IA. This is the current along z axis, and we use another subscript which will become clear from this, IB ZY. So these are the current flowing along the z axis in the volume elements where A and B, when they are placed, we consider the plane to be the YZ plane. That is to say, this is this current and this is this current. So if we consider this, we can call it that IA ZY, and the area is delta y delta z. So we have used two definitions of the dipole moment. First is through via magnetization. This is magnetization, this is dipole moment per unit volume multiplied by volume. So this is the dipole moment of this volume element A. And we have used another definition, that is the dipole moment is equal to current time, circulating current times the area. So the area that is of relevance is this, and which is delta y delta z. Similarly, if we use this to for B, and for B we will have mx at B delta V is equal to IB ZY delta y delta z. Now notice that A has this coordinate and B has this coordinate. We want to express this in terms of the reference point A. So what we need to do? We need to expand it in binomial series and in Taylor series and retain the first term only. So the So to say, mb at x is equal to mx at x y plus delta y z. So this can be written as mx at xyz plus delta mx delta y times delta y, and plus higher order terms. We are neglecting this higher order terms which are neglected. So to the first approximation, this is the value of mb. So we write it as mx plus delta mx delta y whole thing is multiplied by delta v. In this same notation, this is equal to mx delta v. Now you see what is the current. The current in the volume element A, the current is flowing along the positive z axis across the boundary. So across this boundary, the current in the first element is flowing along the positive z axis, while this current is flowing in the negative z axis. Here we have assumed the standard convention of circulating things, that since we are looking at the xy plane, yz plane, we are looking down the z axis, x axis, and anything in anti-clockwise sense is treated to be positive. So in this case, when we look down the x axis, this is the anti-clockwise circulation, so they are treated to be positive. So if we want to find out what is the net current flowing in the positive z direction across the two volume elements displaced along y axis, what will go? So let me rub this part. Net current along z direction across the boundary between A and B. These are the two volume elements displaced along y-axis. This is I z y. This is equal to, this is I z y a minus I z y b, because IZA in the positive z direction and IZB is in the negative z direction. The things become simple if we multiply it by delta y, delta z. So this is delta y, delta z. So this is simply mx for this, for IZA I have used this one, IZA, and for IZB I have used this expression, and and we see on simplification that it is minus del x del y, and yz cancels yz, I have missed a factor, delta y. So this should not be there anymore. So it's a wrong calculation. No? Okay. For IZA, del x del y is delta v and times delta v. If we cancel this, we get IZY is equal to minus delta mx delta y, yz cancels out, so left is delta x delta y. This is one important relation. So what we find that if we consider two similar volume elements which are displaced along y direction, then the net current that is flowing along the z direction across the boundary between these two volume elements is governed by this. So let me write this. IZY is equal to minus del mx del y delta x delta y. Now we consider the two volume elements A and C which are displaced along x direction. Then we should look the situation from the positive y direction, and the current is in this direction. The current circulating current is in this direction. This current is IA ZX and this is IC ZX. So these are the current along z direction along two volume elements displaced in x direction. So the x additional subscript x is used. You see that the current due to the A is in the downward direction and current in C is in the upward direction. That's why the corresponding result will come out to be IZX is equal to plus del my del x delta x delta y. Because this plane is the xz plane, so the direction perpendicular to this is my direction, so we are considering my, the y component of m. They are displaced along x direction, so derivative is performed with respect to x. In the earlier case, the current was positive in this element and negative in this element, and in this case the current is negative in this element and positive in the second element, so there will be a change of sign. So if we consider net current along z direction, IZ, this is IZX plus IZY. This is we immediately see that the quantity within the parenthesis is the z component of curl M. This is nothing but curl of M's z component. So what we do, we divide it Iz by delta x delta y. So this is the current along z direction across unilateral length. So to say this is jz, but we use jmz to remind us this is the z component of the magnetization current density. Because why magnetization? Because this circulating electron leads to the dipole moment, which in turn produces the magnetization. So to say, we find that if we consider the other contribution, we could come to the relation that curl of m is equal to jm. The relation that we advocated at the beginning of the talk is this. So this is a calculation which explores the physical insight of what is happening within the material, and we come to this current density. So the problem is that if we know the magnetization, then we can find out a corresponding current density Jm. If you know the current density Jm, we can calculate the corresponding vector potential or the magnetic field by using Biot-Savart law. So the problem of finding Bm has been addressed in a simple way. In the next class, we shall show that this definition is not mathematically correct one. It lacks one more point that we will be considering in the class. That is, this calculation has considered only the effect arising within the mass, that is within the volume. The surface effect has not yet been considered, which will be our point in the next class.